All right, this was really refreshing. Good morning, everyone, and welcome. Welcome to the third session on advanced technologies for water reuse. Wastewater reuse is one of the most important strategies to augment water supply together with seawater desalination, which we heard a lot about yesterday. And this session will include 2 talks about new concepts for wastewater reuse and 2 talks that are talking about how to take technologies in early stages and implement them later on in wastewater reuse schemes. So we would like to briefly introduce all speakers. By the way, Andy and I are co-chairing the session and giving talks.
Very efficient.
Okay, so our first speaker is Tzachi Kat. Tzachi is a professor of environmental engineering at the Colorado School of Mines. He is also a co-director of the Center for a Sustainable West and Mines, and he holds a joint appointment with the National Renewable Energy Laboratory. Adi Radian is an associate professor at the Faculty of Civil and Environmental Engineering at the Technion in Haifa, Israel. She completed her PhD at the Faculty of Agriculture of the Hebrew University in Soil and Water Sciences and carried out her postdoctoral fellowship at the Biotechnology Institution of the University of Minnesota. In fall 2016, she opened the Environmental Soil Chemistry Lab at the Technion. Adi.
We're going to hear from Megan Plumley. Dr. Megan Plumley is the Director of Research for the Orange County Water District in California, where she oversees a team of research scientists and engineers conducting applied studies to support the district's operational needs. And we're going to hear from Dr. Ines Zucker, which is an associate professor at the Faculty of Engineering at the Tel Aviv University. She has background in mechanical engineering, materials engineering, environmental engineering. Also did her postdoctoral fellowship at Manny's lab at Yale and opened her lab at 2019. So we're going to start with Tzachi's talk. Tzachi, you can come to the podium.
Okay, so today I'm going to tell you a story about a water treatment plant on wheels. This is a project that we started 3 years ago, and we built a system that runs 24/7 and demonstrate potable reuse. So I'll start quickly. We don't have water, and we are experts in contaminating the water that we have, and as a result, we're, tapping, deeper aquifers, and we see more and more big cities and small towns running out of water from South Africa to India to Southern California. And so we have to think where we are taking the next gallon of water. Of course, we can do seawater desalination, but that doesn't help inland communities. In Israel, probably it's easier because you're closer to inland, but here it's more difficult. We can tap deeper wells, but that comes with a cost, with energy, and with higher salinity that require us to go back to desalination. And of course, that we can do water reuse, and for a very long time we're doing non-potable reuse. Israel is a great example of how you're doing it well, and more we are pushing into potable reuse. And under potable reuse, there are 2 options to do indirect potable reuse, going through an environmental buffer to remove some of the yuck factor from the water, and more we are doing direct potable reuse, so pipe to pipe, taking water, blending them with other water or as is, and doing it. And I didn't have to be persuaded to do research on direct potable reuse. When I was a graduate student with my dear advisor, Professor Childress, she pulled me into research funded by NASA on potable reuse for space application, long-term space mission to Mars. And it was fun. So The motivation this time was a call from colleagues from Colorado Springs Utilities, a large utility in Colorado. They wanted to demonstrate to their customers that the future will be potable reuse, and they asked me if I want to join, and I said, sure. I think we can do a lot of good things, demonstrate innovative technologies, developing new methods, and as during the process, we started involving the Colorado Department of Public Health and Environment. So they were at the time working on developing DPR regulations for Colorado, which last year Colorado became the first state in the U.S. to regulate DPR. And of course, as professors, our mission is to train the next engineers and scientists, and knowing a little bit about designing, building, and operating pilot systems, and knowing that if you put it on wheels, it probably will get better utilization, we moved forward with developing what we call the Pure Water Colorado mobile demonstration for DPR. And we build it in a form of test bed where people can do collaboration in the research. So this is an advanced treatment system with many processes sort of pushed into this long and tall trailer, and with recent capability to compare side-by-side carbon-based versus RO-based direct potable reuse. So this is a quick trip into the trailer. First thing that you'll see on the left, sorry, the floor was not so clean, but amide filter from Israel, self-cleaning, followed by ozonation, several biologically active filters, carbon, and going into ultrafiltration system. Initially, it was microfiltration. We all the time changing technologies. Again, then moving to the right, a small CCD or CCRO RO system for parallel desalination, adsorption columns with different media, and then UVAOP and disinfection. Overall, what we have there is a main train that treats around 7,000 gallons per day of reclaimed water, turn it into drinking water, fully automated, remotely or locally controlled, and a small side stream reverse osmosis system that's much smaller, that also fully automated and can be operated remotely or locally. So, I called it an ultimate test bed because it can bring, and it already brings, different disciplines to work together on one platform. We already created a very unique collaboration with different universities and national labs, and we were able to pull together many industries to help us both support the research, but also provide unique equipment for this trailer. We deployed first in June of 2021, just coming out of COVID in Colorado Springs. After a year, we moved to city of Aurora, just east of Denver. Then after a little bit over a year, we moved to a city of Littleton, Inglewood, and recently we moved to Denver Metro. Unique things about it is that these first three are small plant, approximately 5 million gallons per day, and they are all tertiary treatment. So what the water that we got into the trailer is relatively clean. And the big challenge started in May when we moved to a 150 million gallons per day wastewater treatment plant that's doing only secondary treatment, and that's very challenging on a system like that. So one of the conclusions is that tertiary treatment is really needed for potable reuse. It's currently supporting more than 7 mainly graduate and a few undergraduate students and 2 postdocs. So again, going into the treatment train, ozone, bath, UF with pre-coagulation. Adsorption with different media, UV AOP, and chlorination, with, again, the side stream of the reverse osmosis that takes water after UF, but return the brine and the permeate back into the system. Was the sort of initial configuration. We recently added a parallel train of UV LED in parallel to low pressure UV. And at the beginning, we operated with 4 GAC columns in parallel, and last year we moved to 2 pairs of columns in parallel, sort of 2 columns in series, but 2 in parallel, 1 GAC followed by ion exchange specific resin for PFAS removal, and the other pair GAC followed by fluorosorb, which is a unique organoclave also for PFAS removal. As we move forward with upcoming project, we will focus more on the comparison between RO-based and carbon-based DPR, and we'll deploy our RO follow again by UV AOP. We packed this trailer with many, many sensors in order to enable, again, and Megan gave a good introduction yesterday in her talk, to be able to do more data science in this trailer. So you can see here that we packed sensors around the ozone generator, many turbidity meters, many carbon analyzer, nutrients, pH, dissolved oxygen, UV, chlorine, a lot of ways to generate many data points as we operate. And of course, in parallel, we do sampling campaigns to look at things that you can measure with these small or the simple sensors. We build a very sophisticated control system in-house, again, remotely control. Most of the time, this is an autonomous system that operates by itself. And when we collect data every 10 seconds, we're generating 2 million data points every day. When we go to 1 second, we generate many millions of data points every day. It, of course, came with many challenges to build something like that, minimizing or maximizing, processes in a small footprint. Height is an issue, so most of the columns, the biologically active filters and the adsorption columns operate under pressure. Because you have a mix of continuous processes with intermittent processes like ultrafiltration that need periodic backwash. We didn't have much money, so we had only 1 membrane. You had to install a few buffer tanks or break tanks in the system in order to facilitate continuous operation. Finding the right size of some processes is not easy. We started with a very oversized UV, but since then we improved the situation. And again, maximizing data collection was, with small number of sensors, but we were fortunate. Hawk, which is a leading company in sensor, put a contribution of more than $150,000 to really make sure that we collect a lot of data. So what project we are currently running in this trailer? The first one is advanced control system, developing of model predictive control, and I'll talk a little bit into what Megan mentioned yesterday with digital twin machine learning. This is research funded by NAWI, DOE, with collaboration with Oak Ridge National Lab and Baylor University. And then we're trying to optimize energy consumption, recovery, a lot of the process control, and I'll give a few examples soon. The other project is focusing more on water quality. This is a project funded by the EPA with unique collaboration with the Water Research Foundation, CU Boulder, and Southern Nevada Water Authority. That's where we do a lot of modeling and validation of water quality improvements. And the most recent project that we have just started, also funded by NAWI, is looking at more challenging water going into systems like that, and more deeply looking at the comparison between RO-based and carbon-based DPR. That's collaboration with Megan and Bill Mitch at Stanford, Carl Linden at Boulder. And that will be the first time that we're taking this trailer outside of Colorado, and we'll deploy at Silicon Valley Clean Water in Redwood City in California. So a few examples. Again, Megan talked about digital twins and how to implement it. And I'll give you a very nice example of how we started doing it in the trailer. And the unique thing about this is that you have to define objective function of what do you want to achieve, what do you want your system to achieve automatically. And in our case, we said we want to minimize energy consumption, specific energy consumption, and maximize recovery. And we started it with a small reverse osmosis system. It's a CCRO, again, technology that started in Israel. The idea is that you concentrate water in a closed loop, and once in a while dump the salt, bring new water, and concentrating it. What you see on the graph here, the top graph, on the y-axis, you have the one objective function of the specific energy, and on the x-axis, you have the conductivity of the brine that you're discharging. So this is the second objective function, and pretty much you want to maximize the concentration, which means that you maximize your water recovery. The other two graphs are the same graphs, but just as a function of how many concentration cycles we're going through. And so you can see here what the computer is trying to do. It starts seeking for an optimal point for both objective functions. So what we want to operate at the bottom point here, highest concentration and lowest energy. And you can see that it starts somewhere here. It says, it's not a good point. It's going up to there and slowly drifting and finding a location here. Now, it takes many cycles of concentration to do it, and one of the objective of the research now is to minimize how many cycles it will take for the computer to seek the optimal point. And what we're going to do is to now take all the processes in this trailer and do the same thing and eventually combine them together. So, one example of the things that we do in preparation for that is we call process and impact identification, sort of dynamically understand how each process is affected by things that happen within the process, but also how one process affects downstream processes. So one example is our ultrafiltration unit. We are backwashing every 30 minutes. It takes around 4 minutes to do it. And we are dosing coagulant ahead of the membranes, and it's a common practice. But when we started operating with it, continuous dosing of coagulant, and that caused severe fouling on the membrane. And what you can see here is that we are accumulating head loss, or we're increasing the pressure because of fouling very quickly. And it was a nightmare because we had to do clean in place every week or even less than a week. But then we found a paper actually from Israel and a group that looked at optimizing ultrafiltration before seawater desalination. And they showed that if you do intermittent dosing of coagulant, actually you can save a lot of headache. And that's what we saw after, specifically, we decided we'll do in every cycle only 10 minutes of coagulation. And you can see that the head loss increase is much, much slower. Currently, we are doing clean in place every only 5 to 6 weeks, which, again, machine learning and digital twin will be able to figure out how long maybe I can run between backwashes much longer, and how long to do dosing. Another example of process impact identification, looking at ozone and how it impacts downstream processes. So here we run experiments where we stop slowly stopping the ozone dosing or reducing the ozone dosing initially for 12 hours and then another experiments for 6 hours, reducing the ozone dose. What we really monitor and we are targeting is very specific ozone to TOC ratio. This is a requirement for direct potable reuse. And of course, if the ozone dose goes down, the ozone to TOC ratios, the TOC doesn't change much, also goes down. But uniquely, you can see that during these time of experiments, the TOC concentrations start increasing. And this increase in TOC and also probably changes in the characteristics of TOC causes severe performance issues in the ultrafiltration unit. And you can see very fast increase in transmembrane pressure across the membrane because of this additional fouling that goes into the membrane. Again, these are things that you cannot do in a water treatment plant or in a wastewater treatment plant. You cannot stop and introduce faults or problems. This is something that you can do in a unit like that. And of course, looking at energy consumption within the trailer, if the ozone dose goes down, of course, the energy consumption goes down. Talking a little bit about water quality going in and out of this trailer, we are running periodic, extensive analytical or sampling campaign, especially before we make water for public events. And we made a few batches of beer. There's one big batch of whiskeys now in preparation. So if you want to add yourself to the list, and so we are looking into what's happening to the water. So I'll just give you a few examples of what we see in this trailer. You'll see many of these graphs. You'll see the process starts here, the influent, slowly going through ozone bath, UF, not much, but then GAC and UVAOP. This is an example of PFAS research. School of Mines is one of the meccas for PFAS research. So on the left, looking of a combination of many PFAS compounds, and you can see that once you go into the adsorption processes, a lot of the PFAS disappears. And on the right, you see those compounds that are now regulated and are all completely removed from the water after GAC. We also do research on disinfection byproducts. Here, example, NDMAs, looking both on the formation and destruction of different compounds, looking at preformed disinfection byproducts and what happens to them when they enter the process. And of course, we're doing research on other emerging contaminants of concern. On the top, the sum of small concentration of different PPCPs. And again, you can see that there's high dependence on GAC to do most of the work. But also that we have to think about, is that the solution, knowing that we need to have more pre-treatment to protect some of these downstream processes. This is all fresh data from the last few weeks. One of the things that we are now involved in research in Colorado is how to prepare communities and utilities to new regulations. And specifically, I'm referring to Regulation 31 in Colorado that talks about improving or maintaining surface water quality. And that immediately means that your discharge quality will have to improve. And the target for Colorado is that by 2037, which is a long time, but for large utility, it's not so long time, we're talking about reducing discharge standards to 2 milligrams per liter total nitrogen and less than 0.2 milligrams per liter of total phosphorus from the levels that are currently. And so as a utility, you ask yourself, so what am I targeting? What exactly I'm going to need to remove from the water? And so let's look at the nitrogen system, the total organic nitrogen, total inorganic nitrogen. When you look at the particulate organic nitrogen, not a big deal. We'll remove it with sedimentation, filtration. Ammonia nitrate, nitrite, we know how to deal with it, hoping that we know how to do it. The question if we're doing it well enough. The big problem is how to remove dissolved organic nitrogen. That's not simple. Same thing you can see on the phosphorus system. We know how to remove particulate. The soluble reactive phosphorus phosphate, we know how to remove. But again, when it comes to the dissolved organic phosphorus, you are in a big challenge. And so when you are a utility that's their dissolved organic nitrogen discharge over years, and you are at 1.5 milligram per liter, and your regulation is going to be 2 milligram per liter, you start scrambling and figuring out, how do I remove this total organic nitrogen? So we started looking at what's happening in the trailer, and this is just total dissolved total dissolved organic. You can see exactly where things are removed, a little bit in the ozone bath in UF, much more in the adsorption columns. And then when you look at dissolved organic nitrogen, again, you see the same pattern. You can remove them. You are operating at this, still hovering the 1.5, 2 milligram per liter. But with good adsorption, you can remove to very low levels. And somewhat similarly, you can see it on the phosphorus, but what you see about the phosphorus is that it's removed a little bit earlier, I think thanks to the coagulation that we're doing, and some of the phosphorus is removed with coagulation and filtration. And so as a utility, you say, okay, so it takes so much effort to reach this level of regulations. What if I'm just going to do potable reuse and solve the problem, and I don't have to discharge? Again, there are water laws and who owns the water, but I think putting so much effort into water, potable reuse is a nice option. The last graph with data is looking at toxicity and looking on bioassays that we are implementing as a way to look at specific biological activity, knowing that with toxicity testing, you can account for mixing effect of different contaminants in the water that you cannot do, and it's more expensive to do when you analyze long list of emerging contaminants. So we are using estrogen receptors and aryl hydrocarbon receptor bioassays to look and actually start comparing between carbon-based and RO-based DPR. And you can see here what they're going into the adsorption column. This is for the AHR bioassay. And very nice destruction during the GAC, sort of removal with the GAC and then destruction with UV-AOP. You can see the same thing with the estrogen receptor bioassay. Also removal, almost complete removal after UV-AOP. And the nice thing is to see what RO can provide us. And you can see that for organic micropollutants, RO-based DPR and carbon-based DPR are not far away from each other. Of course, that if you're going to operate something like that in Arizona, where you have salinity in the water, it opens completely different discussion. So RO-based and carbon-based, so far not so different. So, concluding remarks, there's a huge benefit in testing different waters on the same platform, taking it from one place to another and testing. Every time that you move to a new place, you learn new things that you didn't think that are an issue when you want to implement potable reuse. And at the same time, very interesting that you have two trains of different processes and you can compare between different approaches. I didn't show much, but I can tell you it's a nightmare treating secondary effluent compared to tertiary effluent. This is something that we are struggling for several months now. And RO is not always the key for successful DPR. I think that will be fun to do it. More deeper research in California next year. Small communities will probably implement things like that, and advanced control system and data, better understanding the data to your advantage are critical for the future of water and wastewater. And I think the important thing that I learned is that managing many projects in a small footprint is not simple. You have different students running different experiments at the same time. Managing who is doing what, not to impact other project is not simple. But it's fun. So thank you, everybody. Most importantly, many students, many faculty involved in these projects. Many local and federal agencies that contributed towards it. Many utilities that even if we don't test there, they contribute. And of course, many industries that made it possible by donation of unique equipment. So with that, thank you so much.
So I'll take this opportunity until the slides come up to also acknowledge Pedro Alvarez that helped put this session together and couldn't be here today. So it's a good opportunity to say thank you to him as well. So I'm used to walking around when I talk, so I apologize if I walk back and forth and you stop hearing me. So for something a little different, I'm going to talk about what we've been doing in our lab in terms of remediating organic contaminants and trying to think about combining different technologies together to try and overcome some of the barriers that are hindering good and efficient and stable water technologies. So I apologize for the stupid AI image, but what I wanted to say here was that we've been talking about separation technologies and moving pollutants from one phase to another. And I want to talk a little bit about the option of also trying to remove them from one phase to another, but also to try and destroy and take care of the whole problem in one system, or to try and combine two technologies together. So I'm going to be talking about both adsorption and destruction of compounds. What we do in the lab is we try to think about ways to adsorb and then degrade either chemically or biologically the pollutants. And we're talking about organic pollutants mostly. So today I'm going to focus on heterogeneous Fenton reactions. For those of you who are less familiar, the classic Fenton reaction takes divalent soluble iron ions, and they activate hydrogen peroxide to create hydroxyl radicals, and that can be cycled back then with hydrogen peroxide, and then the divalent ions come back up. Let's see if and so this is a very efficient way of producing radicals that can break down organic pollutants. There's a few problems with this reaction. First of all, the pH needs to be quite low for it to produce the hydroxyl radicals, and iron sludges also form during the reaction, and it's very non-specific, which means that the hydroxyl radicals will essentially attack any organic compound in the system. And so some of the work is shifted towards heterogeneous Fenton reactions, where the catalyst is a solid iron oxide, as you can see here. This reaction is slower. Usually the iron here is trivalent, so the rate of hydrogen peroxide decomposition is slowed by 2 or 3 orders of magnitude, and there's several reactive oxygen species that come up. But you can work with this at a wider range of pH, and you can take the catalyst out more easily. So a lot of work has been done on trying to use heterogeneous Fenton reaction as an advanced oxidation process. And we in our lab have been working with clay minerals and oxides as sorbents, and the idea was to try to combine the two technologies together. So can we remove the pollutant and then use the adsorbent also as a catalyst. And the reason we use clay minerals is that they're very low cost, abundant, not toxic. They have a huge surface area. The surface area of Montmorillonite, which is this clay here that we use, is about 800 meters square per gram, which is about 2 basketball courts for 1 gram of clay. And so it can be used as a sorbent very efficiently, and we can also alter the surface properties to make it more specific towards specific targeted pollutants that we want to address. And so the idea was to take iron oxides, precipitate them on the clay mineral surface. The clay would be used as a support and as an adsorbent, and the iron oxides can be deposited in nano-size form, and that would create a large surface area, very reactive, so both as a catalyst and as an adsorbent. And so we started out doing that. This is work done by one of my postdocs, Dr. Maria Joffe, and she synthesized several clay minerals, deposited the iron oxides in different species of iron oxides on the clay. We looked at hematite, we looked at magnetite, and we also deposited amorphous iron oxide on that clay. We did a lot of characterization. I'm not going to go into this here, but just to show some of the results with our model pollutant. So we used initially phenanthrene as our model pollutant, and what you can see here are 2 graphs. One is the degradation of phenanthrene, and the other one is the decomposition of hydrogen peroxide. And you can see that there's not a great correlation between the amount of phenanthrene that's being degraded and the amount of hydrogen peroxide that is being decomposed. So some of the surfaces activate hydrogen peroxide decomposition, but that doesn't mean that it creates the right radicals to degrade the phenanthrene. And the composite, or the iron clay composite that worked best, was this composite here, which is amorphous iron oxide with a lot of hydroxyls, iron oxyhydroxide, which degraded phenanthrene quite well, and the amount of hydrogen peroxide that was decomposed was quite low. So just to look at the material a little bit, this is a TEM. You can see the small nano-sized amorphous iron oxides. It gets kind of this orange hue. And we followed the activity of this catalyst in the presence of phenanthrene and hydrogen peroxide. And you can see here, again, the decomposition over time, or the destruction, degradation over time of phenanthrene. And you can see the decomposition of hydrogen peroxide. So you need a very small amount of hydrogen peroxide, and you get quite nice degradation of phenanthrene. And we looked for byproducts in the solution. We looked with GCMS, and we looked at the EEMs, and we couldn't find any byproducts coming up. And so our thoughts were that maybe the rate limiting step was the diffusion of phenanthrene to the surface, and then the degradation occurs quite quickly, and that's why we're not seeing any byproducts. We looked at the different reactive oxygen species that could be found in this system. We mostly found hydroxyl radicals and singlet oxygen. And using different quenchers, we could identify that the singlet oxygen is the one that is most efficient in degrading the phenanthrene. So we have TBA, which quenches the hydroxyl radicals, and then sodium azide, which quenches the singlet oxygen, and the control without the quencher, and you can see that when we add the sodium azide, then there's no phenanthrene degradation. And one more interesting thing that we found is that if we add hydrogen peroxide before the phenanthrene, we can still get quite nice degradation. So we can add hydrogen peroxide, and it gets pre-adsorbed to the surface, but it doesn't decompose. And then when we add the phenanthrene, then phenanthrene gets degraded, which is quite interesting. What we think is happening is that the phenanthrene reaches the surface where the hydrogen peroxide is complexed with the iron oxide, and then actually the whole thing is activated. And we did this kind of cycle experiment where we added hydrogen peroxide and the catalyst and phenanthrene, and then we after phenanthrene was degraded, we spiked with more phenanthrene without adding more hydrogen peroxide. And this is the graphs that you see down here. So every time we spiked with phenanthrene, we can see the degradation. And we can also see the decomposition of hydrogen peroxide here. And we can see that every time we add more phenanthrene without adding more hydrogen peroxide, it gets decomposed, and kind of linearly as well. So we're thinking that there's some kind of system there where the hydrogen peroxide is complex with the surface, and then the phenanthrene comes in. And this got us thinking that we can play around with the type of pollutant that comes close to the surface, and that can alter our system. So we were looking at catechol in the system, because catechol, which are the species where you have a benzene ring with two adjacent hydroxyl groups, can complex with iron and reduce the iron, at least in solution. So we asked whether, if we add this to the system, will this reduce the iron on the surface of our clay? And this could initiate faster hydrogen peroxide decomposition or activation, and can enhance the formation of reactive oxygen species. So the question here was, will the catechol, or in this case the gallic acid, reduce the iron on the surface of the clay, and will that enhance the decomposition of gallic acid? So the answer is yes. When we add gallic acid to this system, we see iron being reduced on the surface of the clay. As you can see here, this is divalent iron in our composite coming up as we add the catechol. And we got this really brown color when we added the compound in, and the thought was that maybe it's polymerizing on the surface due to some side reactions. And when we add hydrogen peroxide, we can see that the hydrogen peroxide decomposes quite quickly in the presence of the gallic acid, as opposed to before when we added and the hydrogen peroxide was quite stable. So this is changing the activity of our oxidant on the surface, and you can see here the correlation between the amount of hydrogen peroxide that's being decomposed and the amount of divalent iron. So if we think about this, if we have a wastewater that's rich with phenols and catechols, this might be a very good system to try to degrade them. So we looked at exactly that. We chose 5 different polyphenols that you might find in olive mill wastewater or winery wastewater. And we looked at 5 different compounds that are a little bit different in terms of structure, and we wanted to see whether this type of adsorption, degradation reaction could work for these compounds. And so we chose these 5 compounds here. Oops, back. Spoiler. So we chose these 5 compounds here that you see. 2 of them have catechols. So it has the 2 here, the catechol here. It has the benzene ring with the 2 hydroxyls. So that's the CC and the DHB. And the other 3 have similar structures, but not exactly a catechol structure. And we looked at the adsorption, and then we looked at the degradation. So in terms of adsorption, you see that each one of them has a different kind of adsorption trend to our iron clay composite, with the 2 catechols having a nice Langmuir type shape. Okay, so reaching kind of a plateau and suggesting that there's a chemical affinity between the compounds and the surface, and the others have more of a linear or S-shaped type adsorption. But most importantly, if you look here, the amount of iron, divalent iron that's formed, it rises only with the 2 catechols and not the other groups. So definitely the catechols can reduce the iron on the surface. And then when we add hydrogen peroxide, you can see very clearly the effect on the decomposition or the degradation of the polyphenols. So in the 2 systems with the catechols that you see here, degradation was really, really fast and significant, whereas the other 3 degraded quite slowly. I should say that after 24 hours, all 5 compounds were completely gone from the solution, but you can see that within minutes, the 2 catechols were gone. So again, we looked at the different species of radicals, and we saw that you can get 3 or 4 different reactive oxygen species, but I want to show the most important point here. We tried to look at the degradation of compounds that weren't catechols, but in the presence of catechols. So we took TCA, which is the least reactive of our 5 compounds, and we looked at the degradation of TCA in the presence of all the others. And you can see that when TCA is with the CC or the DHB, which are these 2 degradation trends here, it degrades really fast. So just having catechol in the system can really induce degradation of other more recalcitrant compounds. So what we're thinking again is going on is that these catechols complex with the surface, reduce the iron, enhance the reactive oxygen species formation, which can then leave the boundary layer and also attack the pollutants in the water. So thinking about this and going forward, we said, okay, we really want to create a platform that attracts the pollutants to the surface, and then we can degrade them more easily. And so we went ahead and we created a composite that had both the catalyst that we were talking about before, the iron-decorated clay, but also we added a polymer that the polymer's job was to attract different micropollutants. And so for this, we chose a polymer that had a beta-cyclodextrin group and a fluorinated biphenyl group. And the idea was to create many different types of adsorption sites for different types of organic pollutants. And kind of the overarching thought was that if we create a sorbent that can adsorb multiple organic pollutants, and then once that adsorbent is spent, we can stop the passage of water, add hydrogen peroxide, degrade our pollutants, and then regenerate our adsorbent for the next step or for further filtering. And then you can get the advanced oxidation process offline, and you don't have to worry so much about byproducts and things coming out of the water that you don't want them to be there, but you can also get clean water. So that was kind of the overarching idea. The composite was created by polymerizing these monomers to a polymer and kind of intercalating the clay within. And we looked at several different compounds. Initially, we looked at 3 different compounds, the compounds in the green, to kind of get an overview of whether it's good for the removal of organic pollutants in general. And then we looked specifically at PFAS removal and degradation, because PFAS are the most recalcitrant family. So just to show the first part, we looked at bisphenol A, carbamazepine, and PFOA, the 8-carbon chained perfluorinated compound. And you can see here the adsorption to all the different parts of our composite. So to the Montmorillon, oops, I keep doing that. Spoiling there. Okay, so to the Montmorillonite clay with the iron oxide, to the Montmorillonite clay with the iron oxide and the beta-cyclodextrin, Montmorillonite clay, iron oxide, and just the biphenyl perfluorinated polymer, and then the whole composite together, or composite. So we can see that each one of the pollutants has an affinity to a different part of the composite. We have carbamazepine, which is in the blue, which likes the clay iron oxide. And we have bisphenol A, which likes the beta-cyclodextrin cup. And then we have PFOA, which is adsorbed to the polymer mostly, but also a little bit to the beta-cyclodextrin cup. So that was in terms of adsorption. We can get really nice adsorption trends. And when we add hydrogen peroxide, we could also see the degradation of all of these 3 compounds, even though their recalcitrance is very different. So we were quite pleasantly surprised that even the PFOA was degraded quite nicely. And I'll show some byproducts in a minute. But again, we can get quite versatile results in terms of the different types of pollutants that we're removing, and we can degrade these pollutants after the sorbent is spent. And we looked at the different reactive oxygen species, and we mostly saw here that the hydroxyl radical was the main species here. And so we moved on to looking at perfluorinated compounds, and we took 7 different perfluorinated compounds that you see here. On the x-axis, you can see the different amount of carbons in each of the compounds. And again, we looked at the adsorption to the different parts of the composite, and we looked at the degradation, which is here. So in terms of adsorption, you can see that the larger, more hydrophobic perfluorinated compounds are removed quite well, whereas the small ones are not removed almost at all, and this is something that comes up again and again, and I also saw it in your results, Tahi. And so the small ones are very mobile, and they don't adsorb to anything. But the small fraction that does adsorb is degraded quite nicely, and as we increase the chain length of the perfluorinated compounds, the degradation decreases a little bit, but it's still 70% degradation. And in terms of what is actually happening, so you can see here after we add hydrogen peroxide, the degradation of PFOA and PFOS, and here this is the TOC, so a little bit of organic or TOC is increased as we add the hydrogen peroxide, and then it decreases again. And you can see here the fluoride ions that are released. So we're not getting complete mineralization. For PFOA, we got about 70%. If we look at the mass balance of the amount of F- coming up, and for PFOS, even less, around 40%. So it's not complete mineralization. We can see some of the six carbon chain perfluorinated compounds coming up in the system, but still we are getting quite nice degradation of these products. But we were still very concerned about the fact that we can't even remove the small compounds, and some of our ongoing work is focused on removing the shorter chained perfluorinated compounds. And so we went back to some of the polymers we've been using in the past that are positively charged. So the previous composite is negatively charged, which makes it very difficult to adsorb the small negatively charged polar compounds. So we took the clays and we added some positively charged polymers to see if we can adsorb the PFBA. We looked at two commonly used polymers. As you see here, polydadmac's been used in water remediation for many years, and this polymer here has some hydrophobic sites, so we tested it as well, and we looked at different types of clays just to see if we can optimize the removal. So polydadmac with montmorillonite clay gave the best results. We're getting up to 80% removal of PFBA, which doesn't seem like much, but it's still more than all of the sorbents I've tried in my lab so far. If we compare it to the removal of PFOA and PFOS are removed much better by this composite. So we're getting 99.9% removal of the longer chain perfluorinated compounds and about 80% removal of PFBA, which is quite nice. So if we manage to take care of PFBA, usually that means that we're also removing the bigger ones. And these are mostly electrostatic interactions between the negatively charged PFBA and the positively charged composite. And we wanted to see if we can also degrade it. So just one more word about that. Most sorbents, when you add in the longer chain perfluorinated compounds, that hinders the removal of the shorter chain PFAS, but not in our case. There's enough room there for all the PFAS, and also as we increase concentrations, we're actually getting an increase in removal. So there's kind of a priming of the surface, makes it more hydrophobic, you get higher removal rates. What is hindering the removal is salt. So higher concentrations of salt is going to completely deactivate our sorbent in this case, because these are electrostatic interactions. So going back to what I wanted to say before, we wanted to see if we can degrade what's adsorbed, because we were using the iron clay composite with the polydadmac, and we can get really nice removal rates, but the catalyst is deactivated, because previously the polymer was sitting in between the different clay layers, but now the polydadmac is interacting with the clay surface electrostatically. It's a positively charged polymer, a negatively charged clay, and that's deactivating our catalyst. So we're getting high removal rates, but about 10% degradation. So this platform is not working for the PFBA, but we did go ahead and test it as just an adsorbent with real water. So we have a groundwater well quite close to where I live in Yokneam, which is contaminated with really high concentrations of just PFBA, which was perfect for our project, but not so great for the locals in terms of the groundwater. High concentration, meaning we have in the initial well water about 1,460 nanograms per liter PFBA. It's really, really high. The production well is closed, obviously. But we took that water and we wanted to see whether this adsorbent could be good enough for the removal of PFBA from the groundwater. We granulated the clay so we could be able to fill out the whole column, like you can see here. And we checked the removal. And you can see we got quite nice results in terms of removal of the PFBA. So this is the upcoming regulation, the black line here. Oh, sorry, this is the quantitative limit, and the red line here is the upcoming regulation that's going to go into effect in 2026. And you can see that after 100 pore volumes of passing the groundwater, we're still not seeing, we're just now reaching the upcoming regulation. So the material is good for PFBA removal, but it's not good for the kind of combination that we were aiming for. So I'm going to sum up what we know so far. So in terms of the material that I presented, the nanosized amorphous iron oxides, they're very highly reactive. We think because of their size and the fact that they're distributed on the surface. The heterogeneous phantom proceeds via surface complexation of the oxidant to the pollutant, and the radical formation we found depends on the type of pollutant in the system. So it's not always the same radicals that we see forming. What we think is that this platform can be used to polish water for reuse, removing and destroying concentrations of different recalcitrant micropollutants, but for the very mobile, polar, persistent, small compounds, this is still not good enough. So we're still working on it, and hopefully we'll find some solutions in the future. So I want to thank everybody in my lab that worked on this. There's a lot of people involved. We do get funded for this, just to answer David Sedlak's question before. Water Authority is on this, and the ISEF is on this, and so we're well funded in terms of the PFAS. And thank you all for listening. That's it.
Hi, everyone. My name again is Megan Plumley. I direct the R&D, or Research and Development program at Orange County Water District, which I'll talk about just a little bit as part of my talk. Well, I'll talk about Orange County Water District a lot, but I mean, as far as the R&D program, I'll mention that as well. So to provide context, I will provide some background on what we do as a water agency at Orange County Water District and where we are, some of our challenges. And I want to talk a bit about innovation at water and wastewater utilities. And then I know folks probably want to see some actual projects and some, actually, I guess, and some results. I do have some results, so I'll spotlight on a couple projects. And I tried to pick projects where sort of the origin story came out of collaboration, right? So something that you would not have done had you not gone out into the world to talk to people, hear ideas, spark a thought. All right, so we are located in Southern California. Orange County is south of Los Angeles County and to the north of San Diego County. So we're in between Los Angeles and San Diego. So we are the darker blue color here. And Southern California is pretty well known for its dependence on imported water supplies to provide drinking water and water supply. But in Orange County, we're a little bit different. We're very, very proud of that. We are 85% on our local groundwater supply. And that's in large part due to our, as far as our agency, the Orange County Water District, our really active management to make sure that we're able to maintain this locally controlled water supply. So as the, essentially we function as a water wholesaler. So we're kind of in the background managing this supply for all of the cities and water agencies in our service area who are the water retailers that pump the water out of the ground and provide it to homes and businesses. So we actually set the price of that groundwater, and that's how we're funded. I actually think it's pretty neat how simple it is in concept. We take our operating budget every year, all of our costs. The last year is always the best predictor of the next year. And then we divide that total cost by how much water we expect everybody to pump as far as groundwater. And the last, history is the best predictor of future years. And that math, the dollars divided by the volume of pumping, that's how we set the price, given that we're, not for profit. So the price currently is $650 an acre foot, and I have the metric there. But yes, using our funny acre foot number. We do have to make up the balance as far as water sources in our service area, which is North and Central Orange County, with imported water. And you can see that costs quite a bit more. So we purchase that water from other agencies, and the cost goes up every year. All right, so we were formed in the 1930s when there was recognition that this groundwater was a precious resource, that it needed to be managed very well since we're so close to the ocean, and so there's that risk of seawater intrusion from overpumping. We serve 19 different cities and water retail agencies in our area. This encompasses about 2.5 million people, so quite a lot of people that are able to have most of their water come from this local groundwater supply. We report up to a 10-member board of directors. They have roles in the community like local city mayors, for example, or city council people, and with backgrounds in law, education, medicine, and some in like engineering, like we have a transportation engineer on the board. As part of our duties, we also protect our rights to the Santa Ana River. We do use that river water supply to augment the groundwater sources through recharge, which I'll talk about. So how do we do it? How do we maintain groundwater as the primary supply with such a large population and all these cities pumping near the ocean? We do it through recharge. So these artificial sources, right, where we add additional water to the groundwater supply. Let's see, just going around the pie. So the natural recharge we get is the green slice here. So that's, just how much groundwater recharge there would be naturally if we did not exist. We also coordinate closely with the Army Corps of Engineers, who operates a dam upstream of us on the Santa Ana River, so they don't release the water too fast as part of their flood control operations. We want them to release it slowly so that we have time to divert it into recharge facilities, so percolation ponds. There's also the base flow from the Santa Ana River that we have all the time. This is essentially 90% about secondary and tertiary wastewater effluent discharges from upstream. So we do actually since we take this river water and divert it into our recharge ponds, now we are dealing with a PFAS issue, since those tertiary effluents carry PFAS, and we've been recharging this water into the ground for many, many years. So it's a water quantity versus water quality conflict, right? We desperately needed that water quantity, so I don't think we have any regrets as far as, it was the sustainable thing to do this recharge, but now we do have this water quality issue that has propagated to certain locations of city production wells influenced by that zone. We do have to make up a little bit of extra recharge to meet our goals by purchasing imported water, but that piece of the pie is getting less and less. And this big piece here we're very proud of is our purified recycled water. So we take 100% of the reclaimable wastewater effluent flows from 2 local, 100% of the reclaimable flows from 2 local wastewater treatment plants that we're partnered with the sanitation district there. We take that water and advance purify it to make more water that we can recharge into the ground as an additional supply. So indirect potable reuse. So all in all, back. Back, okay. I did it again. Pointer. If I say the word somehow, that helps. So all in all, our typical average annual recharge, about 340 acre feet per year, or I tried to do the metric conversion. Maybe I should have done million cubic meters. I think I saw that elsewhere, but for about 400,000 megaliters per year. So a lot of recharge. And here's a nice pretty picture of some of our recharge facilities. You can see the river Santa Ana River in the background, and some of our off-river facilities where we're diverting the river water into these ponds for recharge, and some more of those here. And then off-screen, there's similar ponds that take the advanced purified recycled water, and those ones look like pretty blue swimming pools. All right, so just a quick slide on the purification system. We take the effluent, secondary effluent. You can treat it. It works. I know, Zahi, you said you had some challenges in your project, but for us, it's actually secondary effluent from the Orange County sand. We put that through a low-pressure membrane system. Some cells are microfiltration and some cells are ultrafiltration because we've started transitioning to the newer type, the ultrafilters. Reverse osmosis, and then UV with hydrogen peroxide. So most of the water goes to those spreading ponds like I showed in the picture. We have 1,100 acres, or about, I think that's about 400 to 500 hectares of wetted lands that we use for recharge. So a lot of recharge spreading ponds. And then about a third goes to injection wells, including for recharge and also for a seawater intrusion barrier. Okay, so given our mission, which is the big umbrella is groundwater management, and then as part of that, potable reuse on a very large scale. Of course, we have no shortage of interesting challenges. You know, with the river system we manage, we have constructed wetlands, endangered species that we have biologists that go out and monitor bird populations. We've got PFAS issues, as I mentioned, we're building 60 different PFAS treatment plants at these groundwater extraction well sites for the drinking water production wells. So lots of PFAS work going on. We have our advanced water purification plant with membrane fouling and high energy costs. Our energy bill every month is, I think, almost $2 million or so, $1.5 million US dollars. So lots of energy to run the RO. Our recharge basins, of course, clog and have to be managed. We do a lot of piloting of new technologies, which you think everyone says 6 months and really takes 2 to 3 years for every project. We've had staff retirements, so we're facing, you know, that issue of folks retiring, and that knowledge kind of leaves with them, right, sometimes. So lots of different challenges. One of the ways that we try to address some of this is through maintaining an active R&D program. It's pretty cool, I think, that we have such a program. Of course, I'm biased because I run that program, but it's not so common to hear of a water or a wastewater agency that has a research group. Sometimes they do, and it just goes by a different name, and you have to talk to them to find out. So I'll say a little bit more about that. But as I mentioned, our agency was formed in the 1930s. We established an R&D department in about the early 1980s and have had it ever since. We were doing research and piloting before then, but at some point you start hiring more staff and coalesce the group into a group and give the group a name, right? So in the 1980s, it was officially an R&D program or department. So we do very applied research. It does need to be very practical and clearly connected back to some challenge that the agency is working on, or some issue, maybe some regulatory driver, for example. So less fundamental research and less exploratory, more kind of practical applied research. And these are some of the fun pictures of different, let's see, what am I showing here? This is our full-scale RO facility, and we have a program where we test new types of RO membranes coming onto the market and sometimes not commercially available yet, like from startup companies, and we can do that at full scale in the plant. This is a closed-circuit reverse osmosis pilot. This is our PFAS. Our R&D program piloted out lots of different medias to absorb PFAS, and that was the basis for the selection of the medias that are going into the full-scale plants we're designing. So a lot of very practical stuff to choose technologies, but also very much a research program collaborating with universities and other partners. These are the constructed wetlands. We worked with Renew-It for many years on this system. They studied fate of different contaminants and other topics in constructed wetlands. So lots of fun research. So when I'm talking to other utilities about having a research program, I like to make the point that, you know, utilities can innovate and do research at kind of different, really varying degrees of investment, right, in terms of how much time and commitment it takes. Absolutely, providing data, samples to research projects like a lot of you perform, having utility staff participate in workshops and conferences and events and advisory committees, that's absolutely important, right? We want to get those conversations going and learn from each other. Of course, a greater degree of investment would be to offer up your site as a test bed, right? There's inevitably going to be some staff time from your utility staff to work with students and professors and technology providers to plumb up a pilot system or to troubleshoot it and work together. So test bedding, of course, takes more time. Sometimes it's initiated by us because there's something we want to trial. Other times the idea is brought to us by a partner and we sort of open our doors and facilitate the project. And then at the higher degree of investment, a more sustained program. So you could say that's what we have, since we have an R&D program with funding and staff where we're on the organizational chart of the utility, and we have our laboratory funds and our staff salaries and all that covered by the utility, as opposed to just being solely supported on grants or something like that. So sort of, I think very practically, so when I was thinking about, okay, what are the practical ways of ensuring innovation in the water sector from my perspective at a utility, it's really through collaboration. So talking to other utilities, meeting with universities, going to conferences, hopefully a lot, which is hard because we have limited travel budget, and I feel like I'm always, trying to get more. And I wish I could send more of my research team to conferences to meet with people like you. But there is some limited travel budget at times. Also, letting technologists pitch their ideas. There's lots of companies, established companies with new concepts, or startup companies with new concepts, and it takes time to say yes, right? But hearing from folks and trying to explain what our situation is and our challenges, and hearing what the technology is, and then trying to see, maybe the fit isn't quite what the technologist was thinking, but maybe we have a different application that could make sense. Volunteering to serve as a testbed site, and then building a diverse team with different partners. So having a dedicated research department isn't required to do this successfully, but it definitely helps, since it does take a lot of time. And so I think having an R&D program within the utility helps a lot, because you can designate people with responsibility for these projects. I've seen some new ways coming up to help ensure utility innovation and continual learning, and these dialogues around new ideas that I thought I would share. I think they're kind of interesting, and I think they've been working pretty well. Some of you may have heard about ISLE Incorporated. They used to be called ISLE Utility. They are not a utility, so maybe that's why they changed their name. But they are consultant teams that can support utilities in different ways, including facilitation and introductions on topics. So basically, it's a safe space for utilities to come together, typically virtually, for the convenience factor and to reduce cost, on specific topics. So what's really neat about this is that they will release a certain topic like brine management and let their utility network know. And then for a relatively modest fee to ISLE, the utility can join this work group, and ISLE will present new technologies they hear about. And it's generally commercially available stuff, but I would love it if they showcased more university work as well. They will showcase new ideas and new technologies and new approaches and get that reaction from the utility group. And then they carve out time in the meetings for all the utilities to go around and share their approaches and their challenges and provide updates. And a lot of organic things spin off of that, right? You find out about a technology, so you set up a meeting with the vendor, which ISLE can facilitate. Or maybe, I heard, and it's international, mostly it's US, but there it is. They set up a special meeting between US and UK, and in one of those meetings I heard a UK utility doing something kind of similar to one of our research projects, right? So now I have a correspondence going with that person. So a lot of stuff that you wouldn't hear about or know about if it weren't for this opportunity. The Bukky Oren Global Water Technologies Consultancy does something very similar. Bukky was, I guess, an executive chairperson of Mekarat in the past, so some of you may know the name. And now he has this firm where he does utility matchmaking. So whereas IL brings like a large group together in a virtual space and also some in-person meetings, Bukky's team will interview the individual utilities to find out what your challenges and priorities are, and then do like a matchmaking one-on-one, and then you'll have like a series of meetings with that other utility. So we've had regular meetings with V10s in the Netherlands, for example, and also Mekarat recently talking about issues like PFAS, and Singapore PUB, and also US-based utilities like Tucson Water. And then the Water Research Foundation is helping us to grow a community of trying to find who are the water utilities and wastewater that have research divisions or innovation work groups and do test bedding of new technologies. So we've named ourselves the Water Utility Research Community, or WORK. This is kind of a grassroots effort by people like me who just want to find my counterparts. Otherwise, I'm kind of an island in my own organization. You know, I work at a water agency. Everybody knows what the operators do. Everybody knows what the hydrogeologists do, what the engineering department is for. But I think when you're R&D, you're always having to kind of justify, what do you do? And why are you necessary? Why are you important to keep, even within your own organization? So it's been refreshing to sort of compare notes with other utility research leaders and kind of share, tricks of the trade. And here's just the map we're starting to put together. We've identified about 50 different water and wastewater utilities in the US and some in Canada that have research groups. So as part of preparing today's slides, I started going through an exercise that I thought ended up being kind of interesting. I took the 30 different projects that we have currently in our R&D program at Orange County Water District. I didn't count ones that are like, maybe it's led by an outside partner and we're just sending them samples. That is a collaboration and a project too, but I kind of just listed the ones where we have a larger role. And I organized them by color with, blue is the ones that we initiated, so projects we decided we needed to do. And then green are projects where we heard about it because a university researcher, a professor, and their students, approached us to work on the project with them. And then in the reddish orange, same but initiated by maybe a technology provider or a consulting engineer. And then I organized them again in the columns from left to right. Left, the things that were projects that are just very pressing, where there was a strong interest for us to accomplish something. So I call that necessity is the mother of invention. And then projects maybe a little less pressing, but, we're intrigued by a concept and want to explore whether it's something we can improve or something we can optimize, so seeking optimization. And then another category of kind of just saying yes, like an interesting project and just agreeing to kind of be a test bed, facilitate someone else's project. And a couple takeaways from me for this was that, and something I already knew, but it's nice to kind of see it in color, I guess, that the universities and solutions providers, the green, the orange, really do play a significant role in helping us be an innovative water agency. These ideas are coming from them, and we're hearing about it because we're trying to get out there into the world and meet people, or they're maybe coming directly to us because they know somebody. But I also thought it was interesting that the first column is just all blue. I mean, it kind of makes sense because these are things that are really pressing, right? So it's stuff that we think is important and an issue that needs to be addressed, so we started doing the project. But it still kind of surprised me not to see any orange and green, so I thought, are the universities and the solutions providers doing enough to actually ask us what our pressing challenges and needs are to help inspire them to work on topics? And after I put this slide together, I thought of one example where this was the case, and it's like the only example I can think of like this. But water, the University of California at Irvine, UCI, has their research center on water called Water UCI, and they actually have a committee of Southern California utilities, and I'm on that group, where they ask us what topics need attention. And we do provide some funding, and they pool our funding, and then they try to go out and get grants to match it, and then they do the project. They essentially have like an RFP they make, and they identify either a UCI or another university partner if they don't have the expertise to do it. So it's really like a utility-driven research program through a university. I don't think I've really seen anything like that before. So that could be in the first column with a green color, but we're not like as directly involved. So the 30 projects here is more things where my team, my research scientists and engineers are working directly on it, and we're not involved in that project. But what it was PFAS related, surprise, surprise. And the utilities wanted to know how it's getting into the sewer shed, because they know PFAS is coming out in wastewater effluent, and they believe that's not just from industries, but they wanted to know from where. And so this UCI project, and they're about to, I think, publish their manuscript, found volunteers, people, just residents at home, and sampled the wastewater from like their shower wastewater, their bathroom wastewater, their laundry wastewater, to figure out where the PFAS inputs are coming from into the sewer from a typical home. So pretty interesting project, and that was asked for by a group of utilities that tried to agree on, one project. All right, couple quick project spotlights. This project on hydrogen peroxide was inspired through a conversation with university professor Martin Reinhardt at Stanford, who had studied this some years ago with a different utility, and it hadn't really gone anywhere. But he still had that in his mind, like there's something here. We initially wanted to look at peracetic acid as an alternative to chloramine during the UF followed by RO process for potable reuse. We add chlorine to make chloramines ahead of our ultrafiltration process, so that chloramine can proceed through the UF and the RO for biofouling control purposes for our potable reuse plant. But we had heard about peracetic acid getting attention as an alternative disinfectant. We wanted to try it, and we kind of had hydrogen peroxide in the back of our minds. The peracetic didn't really work at all. It took like a couple years to figure that out, as it does with piloting. So we ultimately landed on hydrogen peroxide, and it's worked pretty darn well. This is a typical graph of performance for an ultrafilter. This is a pilot scale system that we used. The blue is the performance the control, the base case, using sodium hypochlorite to make chloramine. And in a typical cycle, this is just about a month on the x-axis. Let's use the pointer. Transmembrane pressure will rise as the membrane gets fouled. It does backwash every 20 minutes or so, but every few days you have to do a clean in place, and then it returns to its initial TMP. But when we run with hydrogen peroxide, shown in orange, it just runs better. It's just happier. The membranes stay cleaner. So we're thinking about where to go next with this project. It's pretty exciting, because this would be a big change in how conventional advanced purification is done with membranes. But with hydrogen peroxide, we don't see any formation of NDMA or the typical trihalomethanes and haloacetic acids. And we already need hydrogen peroxide for our advanced oxidation process. And so we've actually targeted it so that, since we want 4 milligrams per liter of hydrogen peroxide going into the UVAOP, we put enough hydrogen peroxide into, at pilot scale, the feed of the ultrafilter, which then has a demand, but then some residual of hydrogen peroxide makes it to the RO, and then that has some demand, and then the residual that makes it to UVAOP would in theory be just what you already need anyways for the exact advanced oxidation. So pretty elegant. I will skip the next project because I'm over time, but this is essentially us trying to get more credit from the regulators for virus removal in the subsurface, so the soil aquifer treatment. We take our advanced purified water and put it underground as part of groundwater recharge. So we do enjoy some soil aquifer treatment, but we don't get much virus credit for it. So we, through a workshop, because we said yes, heard a retired regulator say that there was a path for doing this in the California regulation, which we didn't understand prior to that. So it really piqued our interest and motivated us to do this project. All right, I will just wrap up. I won't repeat myself here. Innovation's important, collaboration's important. Thanks so much for your attention.
Okay, Thank you very much, Megan. It was a lovely talk. And we are ready for the last talk for the session, which will be my talk. I'm going to talk about selective nanocomposites for water decontamination and reuse. So just before I start, I want to take a minute or two just to outline the research that my lab has been exploring in recent years. So we focus on nano-enabled water treatment, and as an example, we develop nanomaterial for heavy metal removal based on molybdenum disulfide nanosheets. I'm going to talk about this later on today. We also look at the dark side of things, and in that sense, we look at environmental implications of nanomaterials, but not only the engineered nanomaterials that we create in lab for the first research program, but also on incidental nanomaterials like microplastic and nanoplastic. In that case, we look, for example, at assessment of absorption and toxicity of microplastic, and joint toxicity, I should say. And then in the last part, we work at advanced oxidation processes, trying to push these developed technology into the next level. For example, we work here on groundwater treatment using ozone in a nanobubble form, so encapsulated ozone. And to give you, okay, so I already said that. I'm going to focus on the first part. So I want to connect to the topic of this research, or to the topic of this session, and briefly go through a scheme where, for example, in central Israel, in the Gush Dan, in the Gush Dan area, we treat. We treat our wastewater through conventional primary mechanical treatment, secondary biological treatment, and then, as you heard today and also yesterday, we spread the secondary effluent over infiltration ponds. They go through physical, biological, chemical reaction, and then after 6 to 12 months, they are being collected and used for unrestricted irrigation. So in that scheme, which we already heard about, I want to highlight two important points that I'm going to address today. One is the fate of trace organic chemicals, for example, pharmaceuticals, herbicides, pesticides, hormones, you name it, and also antimicrobial resistant bacteria and genes. What is their fate? We want to eliminate their presence because we want to reuse the water for irrigation. Another important point is that we want to augment the wastewater amount. For example, we can receive to the municipal treatment plant industrial waste, but then we need to make sure that we have the proper pre-treatment before. For example, if we look at the printed circuit board industry, in that case, we're talking about large amount of wastewater that can be released to the municipal treatment plant. However, we need a pre-treatment to remove heavy metal and precious metal from this water. So I'm going to touch these two today. And broadly speaking, I want to go through, the design of two-dimensional nanomaterials for absorption of heavy metal. In that case, we're using molybdenum disulfide, and for catalysis and removal of trace organic contaminants. In that case, we use manganese oxide nanosheet. In both cases, the focus is given to two-dimensional nanomaterials. Then we want to go over the requirements for implementation. Let's say we have these nanomaterials. How do we implement them in large scale and then demonstrate the application? So that's the, let's say, the logic scheme of the talk, but today I want to start from the middle because I want to talk about the requirements for implementation, not necessarily for my own development, but in general. In case that you have a nanomaterial that can be used for water treatment, what do you need in order to implement it in larger scale? And there are many barriers for implementation, which were highlighted in many review papers, starting from upscaling and cost. However, this problem is expected to decrease over time because of the widespread use of nanomaterials in different industries, not necessarily in the environmental context. The second challenge, or the second barrier, is the maintenance. We want to make sure that we can recover the active nanoparticles from the treated water. We want to regenerate them, we want to reuse them, and third, we want to avoid any environmental and health risks. This is also important because once we shrink the dimension of a material, then different phenomena occur. That's what make nanomaterial really appropriate and really reactive, and therefore they might have negative aspect in that case that we want to avoid. And as I said, this was highlighted in different reviews over the years, and we want to make sure that whatever development we work on, we overcome this barrier. And one essential tactic to overcome this barrier is to have a strategic pairing of the nanomaterial with a less mobile platform, something that is much larger and that will make it much easier for use. So if we want to put it on a scale of time, on a scale of time, while the focus was given so far to nanomaterial design, now we want to focus on strategic pairing to platforms in order to allow practical application. So my lab came up with this platform selection guide because it's important that we will select the appropriate platform for the application or the type of nanoparticles that we use. And this criteria include the effectiveness criterion. We want to make sure that once the nanoparticles are immobilized on top of larger platform, it will be at least as good as it was then as compared to suspension form. We want it to be sustainable. We want to regenerate and reuse this complex, this nanocomposite with minimal leaching of the active component, and we want it to be scalable. We want it to be compatible in large treatment plants. So we took this criteria and we conducted a full critical analysis of top platform to support nanoadsorbents. We just took the literature that is relevant where metal oxides nanoadsorbents are being used, and they are coupled with active platform. And by saying active platform, I'm talking about platforms that are capable of removing pollutants themselves. For example, membranes, sand, activated carbon grains, ion exchange resins, and so on. So these are the active platforms. So we conducted this analysis. And now I want to quantify briefly what we achieved. So first, looking at the effectiveness criterion, as I said, we want to have minimal effect of the platform. We ranked all the relevant literature, and what you can see here very nicely is that activated carbon is almost always above 1. This is the desired area where nanomaterial on the support is more active than the nanomaterial in the suspension form. The reason for that is that we prevent aggregation, and we allow separation and reuse of the nanomaterial. Second, we look at the sustainability criterion. However, this is much harder to account for. We want to make sure that we restrain the nanomaterial separation. However, the literature does not really report on the leaching of the nanomaterial. Only 20% of the literature that was relevant actually reported on this value. So instead, we combined theoretical calculation of adhesive forces in order to rank these active platform into low, medium, and high ranking. And then we looked at the scalability criterion or the commercial viability. And we divided into 3 categories, looking at the raw material score, production score, and compatibility to larger systems. And when we combine all of these together, we can definitely see that porous carbon-based support are the best available platforms for nanoadsorbent. And this work was highlighted in Environmental Science Nano, and from this point I want to continue. So we always want to immobilize the nanomaterial that we develop to larger platforms, ideally to carbon-based materials. So now I want to talk about material design and some fundamentals, starting from the first nanoparticle that we work with, and that's molybdenum disulfide. We're basically talking about a nanosheet. It is drawn here like a nanosheet. It goes through the wall. So we have the molybdenum in the middle, sulfur at the top, sulfur at the bottom. So you can imagine a rug or a mat that is completely covered with sulfur atoms. And that sulfur is actually really, or can selectively absorb heavy metals through Lewis acid-base soft-soft interaction, right? The sulfur is here, and therefore it can absorb cadmium, mercury, silver, gold, and so on. So we took a closer look on molybdenum disulfide, and I wanted to start from the very first project, actually, which was beginning during my postdoc. Here we synthesized, or we electrospun carbon fiber mat. You can also buy it. It's commercially available. And then we used the simplest scalable synthesis technique that we can use, and that's the hydrothermal synthesis. We basically use an autoclave where we put inside the support material, in that case carbon fiber. We put the precursors, solvent, close it, put it in the oven, take it out in the morning, and now you have your nanomaterial. So we did that using different methods where the precursor and the solvent type changed. We eventually get this mats, black mats, and we expect to see in SCM images this lamellar structure, which stand for the nanosheet presence. And that's exactly what we got. However, it was very different when we changed the type of precursor and type of solvent. In one case, we got long aligned sheets. In the other case, we got short aligned sheet, non-short aligned sheet. And you can also see from afar that the yield completely changed. In some cases, we have a lot of molybdenum disulfide on the surface of the fiber. In some cases, not. But what was really interesting is that the synthesis method affected not only the characteristics, but also the performance. Here we look at the mercury removal kinetics and the adsorption isotherm, and we can see that they're completely different. For method 3, we have a very high removal rate. Another interesting fact is that the theoretical mercury adsorption capacity on the molybdenum disulfide is only 2,500. It's a lot, but as compared to what we see here, it's only 2,500 milligram per gram. So in method 3, we have additional mechanisms that are involved in the removal of mercury. And this is something that we wanted to investigate. It was, we found that it's highly related to the crystalline structure of the molybdenum disulfide. It appears in two phases typically. One is the 2H semi-conducting phase, and the other one is the 1T metallic phase. And this 1T metallic phase actually results in redox reaction. And in that case, the molybdenum disulfide, our active sorbent, is basically spent. It's been oxidized to molybdate ions, which are just leached to the solution. And on the other side, the mercury is being reduced, and now it's more volatile. So this is a not desired reaction. We want to make sure that adsorption is what actually occurring, and we now eliminate this reaction by generating only the 2H phase, and we have also indication that we keep tracking to make sure that this reduction does not really occur. For example, pH decrease will immediately tell us that this redox is occurring. Relative reduction in the 1T phase, also leaching of molybdenum, if it's different, if it's higher in presence of the contaminant, then it means that we don't only have physical leaching, which is just related to the adhesive forces between the support and the molybdenum disulfide, but also it is related to molybdenum dissolution through this reaction. We can also look at the elemental mercury appearance. And yeah, this was about the mechanism. I will go very briefly through the rest of the optimization of molybdenum disulfide structure property relationship, but we control the interlayer spacing by introducing intercalating agent that help us to improve the kinetics of the adsorption rate, and we can see here that the kinetics increases in presence of PVP as an intercalating agent. We look at controlling alignment using CVD technique, and we also learn a lot about the effect of crystallinity, amorphous structure versus non-amorphous structure, which tremendously affect the adsorption capacity, the leaching potential, and also the mechanism, the adsorption mechanism itself. So with that in mind, this is a much more mature project as compared to the second one. So the second nanomaterial that I wanted to introduce you to is the manganese oxide, again, nanosheet in an alpha phase, which we deposit on sand. And in that case, we use it as a catalyst to generate sulfate radicals. We basically expose this complex, this nanocomposite, to proxymonosulfate, PMS, to generate the sulfate radicals, and then we have the degradation of different type of trace organic chemicals. This is an interesting approach, or a little bit different approach than a typical AOP where hydroxyl radicals are being formed, because the sulfate radicals are much more selective. That means that we can tailor the reaction and target specific contaminants. We can push this a little bit farther by introducing this or immobilizing this manganese oxide on activated carbon, because in that case, we will also have this bite and hook mechanism where the target contaminant will first adsorb, be in close approximation to the sulfate radicals, and then we will have better rates, very similar to what Adi showed us earlier. So it worked nicely for sand. We deposited the manganese oxide, by the way, in a similar hydrothermal reaction. We showed that we have this alpha phase, and I will show you activity in a slide or two. However, on activated carbon, it was not really successful. And that's, we have very limited deposition of manganese oxide on activated carbon. And the reason for that is that we have lack of surface functionality and the fact that we have hydrophobic activated carbon surface. So next we try to optimize this coupling by having a pre-treatment to the activated carbon. For example, sonication improved the wettability and therefore the deposition rate, and also acid treatment, among others. We also look at different types of activated carbon. For example, marula-based activated carbon or coconut-based activated carbon resulted in much higher yields. And this, of course, was correlated to the presence of surface functionality of these activated carbon types. And we went back to sand, and we just wanted to prove the concept, which worked really nicely. We packed the catalyst on top of sand in a column. We had this feed solution, which included the contaminants and PMS, and we showed that we can remove, both in tap water and in wastewater, different contaminants like carbamazepine, iodinated contrast media, caffeine, antiepileptic drugs, and so on. We can also see that we have low amount of leaching of manganese, and the PMS is still decomposing over time. In the last part, I want to talk about potential application. Let's say that we already optimized these nanoparticles. Now, what's next? What do we need to do in order to use it in practice in wastewater treatment plants? First, and this is a very important part, which we struggle with in the last year, is the upscale. Instead of synthesizing 10 grains of activated carbon with our active component, we want to generate a kilogram of that in a single synthesis. Second, we want to demonstrate operation in real-world water matrices, not in clean water that is spiked with our contaminant. We also want to have competing contaminants, ions, and so on. Then we want to design a flow mode filter reactor, which will allow us to do dimension analysis and to upscale the system in order to achieve pilot-sized reactor. And then we want to assess stability in long-term operation and compare it to the best available technology. That's the plan. It's a huge plan, and I'm going to show you some of the results. So first, we coupled the molybdenum disulfide on top of activated carbon, and we wanted to prove that it can be used as a multifunctional adsorbent. The activated carbon will remain active, although it has this coverage of molybdenum disulfide, and it will absorb organic pollutants, while the molybdenum disulfide will absorb inorganic pollutants. And we were able to show that simultaneous adsorption by using mercury and methylene blue as model pollutants. We also show minor effect of background ion and great operation in presence of complex media. In that case, we took contaminated groundwater with mercury and other materials from a site in Israel. And we also show efficient removal of mercury in multiple cycles with minimal molybdenum leaching. So in terms of the upscale, we have different stages that we wanted to accomplish. First is that we want to increase, in the same synthesis, we want to increase the amount of activated carbon while holding the precursor amount and solvent amount the same. Then, after we have this optimal maximized ratio, we want to increase the content of both activated carbon and precursor at the same synthesis, and then we increase the batch side or the reactor side. So these are some results from the last month for the first part, where we increase the activated carbon amount, and actually it came really nicely. What we see here is that the thickness of the molybdenum disulfide layer is decreasing when you increase the activated carbon amount, the platform amount, with the same, while holding the precursor amount the same. It makes a lot of sense. It's still very active, so when we look at the adsorption potential, it just goes up and up and up until an optimum point. We also see that the leaching is going down and that the yield is increasing. In that case, by the way, all the adsorption tests were conducted with silver and not with mercury. In terms of the manganese oxide on activated carbon project, we already have a site where we plan to implement this technology. This is being conducted together with Professor Jörg Dreves from the Technical University of Munich, and we're going to use an existing pilot plant named in the city of Steinfurt, and the project called Newtwasser. But beforehand, as I mentioned earlier, we want to examine in a flexible reactor in lab the different operational parameters. So with that in mind, I want to summarize what we saw so far. So we have a sustainable use of two different nanomaterials for contaminant removal, which can be used for wastewater purposes or wastewater reuse. In terms of material design, we optimize adsorption through controlling interlayer spacing, nanosheet alignment, crystallinity, and so on. Be able to couple the nanoparticle with the support in a scalable synthesis procedure. We have much more understanding on the mechanistic on the mechanism of the interaction, and we want to minimize undesired reaction. And we have demonstration of this nanocomposite use in practical application, including multifunctional absorption of organics and inorganics, and this bite and hook mechanism. I always put these very simple illustration when I talk about this topic, because I really believe that we should focus not only on material design, but also on process design, and we should take advantage of the knowledge accumulated in these fundamental studies to bring them to practical use in a larger scale. Yeah, and with that, I would like to thank my research group and the funding agency, and yeah, I think we're ready for the discussion.